So welcome to the pre-recording of lecture 10 of Introduction to Symbolic Computation. Today we look into the execution efficiency of Python functions and what we can do about relatively slow interpreted Python functions. So there are two things we can do. We can apply a vectorization, which is essentially using the data structures of arrays and the built-in operations that are available. And the alternative is to use Cython, which which modifies the Python code and which is compiled. Okay, so let's start with the motivating function. So we have seen pi almost in every lecture. So we started from the symbol pi. Here we look at the actual meaning of pi as the area of the unit circle. And if we want to approximate pi from scratch, then we can do this by computing by computing the area. Here the area of the quart of the circle. So we go from 0 to 1 and we only see the positive square root. So this expression here is exact. So this you could take as a definition of the pi over 4. The expression at the right is one could see this as an averaging of the square root taken at equidistant places between 0 and 1. This is definitely not the best way to approximate pi, but it is a very good example for our purposes. It's relatively simple. So in Python it can be coded up in one line. And we can crank up the computational cost, by increasing the dimension n. So the parameter n determines how many square roots we have to take and how many numbers we have to add. Okay, so how do we do the timing? It's good to distinguish between small and large computations. Small computations are almost instantaneous, in the order of milliseconds, so we don't really notice that something ran. If you do this, looking at times you can actually time in the order of milliseconds, but the timers are often too sensitive and you will see fluctuations. A better approach to time small computations is to run them in the loop and also look at the average execution times. For large computations where it takes seconds at least, then you set a timer at the start of the computations, you do the computation, and then at the end of the computations you stop your timer and you compute the elapsed time of the central processing unit. So you can also measure other times, but typically we are interested in how much the central processing unit worked. So we will see that for for a pure Python code, that the computations are rather slow, and that gives Python a rather unfortunate reputation of being not really well suited for scientific computing, which is of course extremely wrong. So one can use vectorization. So our first implementation of our approximation for pi will be using a list comprehension. List comprehensions are very convenient, very powerful. Lists are very versatile data structures, but arrays are so much more better suited, and arrays and vectors are here the same. So we refer to arrays when we talk about the data structure. So arrays are different from lists in the sense that every item in an array is of the same type. So this allows the computer to compute efficiently the index of any element in the array. So running through all the elements in an array goes a lot faster than running through a list. So in the previous, in not the previous lecture, but in our previous session, so lecture 8 on shared references, so when we were using functions to store data, we actually use the fact that when you declare a list, you declare many references, many pointers, one would say. Okay, so work with vectors. So vectors are arrays for which we have the arithmetical operations defined. Also, the functions like the square root can be vectorized. And if we look at this sum here, we would actually, so if you look at what happens in the sum as it is defined here, we compute a point 1 minus k over n, where the k over n is square. We take in the square of it. Then we take the square root. We do this for k equals 1, k equals 2, k equals 3, all the way up to k equals n, and we add up all these numbers. So we do the computation of the argument of the square root, we compute the square root, and then we do the sum. 3 operations. Now we rearrange the operations. So we do the making of all the points all at once. So we make a vector of equidistant points in the interval 0, 1. So that's what the k over n does. We apply the square root function to the entire vector. So that's the other vectorized operation. And then the third operation is to apply the sum to the evaluated points, evaluated by the square root function. So what is the main benefit of this? So in the list comprehension, we have an explicit loop for k in range 1 to n. So that's an explicit counter, which the counter is actually a Python integer. If we run a vectorized function, we also have an index, but the index is hidden to us, and the index is already a machine type integer, not anymore a Python integer. The other important thing is that all the functions that we are running are actually optimized and they are compiled. So we are running a function that is directly given to the CPU in machine code. So when we run Python code, perhaps I should emphasize that a little bit more when I talked about the interpreter. So when you execute Python code, the instructions, the high-level instructions, first have to be translated into machine code. So that takes time as well. And along this translation, there is a lot of error checking that needs to happen. So the translation process from the high-level code to the machine code has actually already happened when we apply vectorized code. So you have the two benefits of the data structures, which are more compact and efficient to manipulate, and also the operations are compiled and optimized. So we will see that for our problem here, that the vectorized code will actually give the most efficient code. There is also Cython. Cython is a variation of Python. It's doing Python the C way. What happens is that you can add type declarations, so then the Python interpreter does not have to guess what type it is. Another benefit is that we can call functions directly from the C standard library. So that means that we also, in our case, we have the square root. So we apply the square root on floats. We will in some sense go to double precision, not the real numbers that are provided by standard in Python in SageMath. So the third benefit is also that Cython code is compiled. I already gave it away that for our small problem, vectorization will be more efficient. So there are two benefits, two different ways of working in essence. So they both share the fact that they run compiled code, but vectorization stays with the Numpy world. So it's actually Numpy code that you are running. So you stay within Python. However, with vectorization, you have to rethink your code. So with Cython, you essentially keep the original control structure. You add more decorators, you add types to it, but essentially it remains the same program that you're working with. With vectorization, you may need a separate especially when your problems tend to be a little bit more complicated, you may want to have some separate verification of the correctness. Of course, if you do scientific computing, as that is your daily practice, then you will immediately start thinking about vectorizing your code. So here I started with I will start in a minute with the presentation in SageMath. There I start with a very basic, naive implementation, and we make it more efficient. Often when one is doing this routinely, one often immediately starts with thinking in vectors. And one has immediately always the efficient tools and the building blocks that are combined. Okay, so that is the outline of this lecture. So we have a problem. So here is our problem. I will put to the formula slide because I will use it when I make the notebook. So let me try to reshuffle things so that I can actually see the formula. Okay, very good. Perhaps you may want to see my face. Well, not so very good then. Let me see if I can still scroll things a bit. No, I can't scroll things. So it will be, okay, so it's still possible. Okay. So here we have the formula. So in some sense, if I run into trouble, I will go to the prepared Jupyter notebook. But let me start from the beginning, so from the very beginning with a notebook that is all blank. So I have my recording of my pre-recording of lecture 10. So in this lecture we illustrate, so in lecture 10 we illustrate vectorization and Cython. So we will vectorize and we will Cythonize. Okay, but let me start with the first code for the timing of Python functions. So I will make a function out of the formula. I already flashed up the function, but let me assume that I'm only seeing the function here. So often it looks very bad that you are always confronted with the final result. So in some sense, this formula here is also a final result. So in numerical analysis, we will consider many integral formulas, and the formulation of a rule like that is there also one of the tasks that will be done in numerical analysis. But here we start from the formula. So how would you do this with the list comprehension? So you can assume that, so let me first work with a parameter n equals 1000, and then I will build up the numbers. So I have k over n for k in range 1 to n plus 1. So it's important that the list comprehension, you have to remember that they end at n plus 1. So now I lowered my value of 1000 to 10. So this gives me the equidistant points from k equals 1 to n. So that is what will be subtracted. So there is 1 minus, and I will also take the square. So this is our warm-up. Perhaps I already typed in too much. If this is not really so convenient, then perhaps I already typed in too many instructions. So I started with the k over n, and then I did the argument essentially for the square root. So here is then the big instruction. I will take the sum of the square root. So I have my list comprehension. I take the square root of 1 minus k over n, here to the power 2, for k in range 1 n plus 1. And that will be divided by 1. And here you see now that I have my square root evaluated already. I want the float of this, so because I want to see pi over 4 times, and 100 here you see that I have 3.14 with corrected rounding. So with 1000, and you see this is still a very straightforward computation, but 1000 will be good, so it's almost instantaneous. So here I have a correct formula. Okay, so now I can define my symbolic sum, so my Python symbolic sum, and I can't resist to write the documentation string. So returns an approximation for pi using symbolic arithmetic. So we've seen here that you see the 1 minus k over n square star star, so I was thinking Python. So you see that I get exact answers. Also the square root will actually be evaluated as it is, and I can copy and paste now. So here you see it. If you have never written Python functions, here is a way to do it. you make sure that you have a formula that is correct, and you use the same letters. So the n here, which was a value, so now the n is a local name inside, known only inside the function. All right. So here it is. Let me execute it to make sure that I have the same number as above. So the Python symbolic sum executed for 1000 should give me, and I see I made a mistake, I have to return. So I have to explicitly return it. Okay, so you see, even with this rather small example, one can make omissions. You will definitely make mistakes if you have to type in everything. So you see the number of brackets, also the floating point conversion. I only got at it because I saw that everything turned out to be symbolic. Okay, so what are we trying to illustrate? We're trying to illustrate the timing of functions. Time it is a built-in Python construction. So the function ran instantaneously. So the time it is apparently not used correctly. I have to enter the string. Okay, so this still used milliseconds. So it's about 60 milliseconds when this ran. So let's take, so that's the first timing. So in a larger example, we work with CPU time. So now I have to check how to do this. Is indeed the function CPU time. So this marks the beginning of time, and I will do the Python of the symbolic sum, but I will require 10 times more computation. So I have now 4 zeros, 10 to the power, and then I do CPU time again, so that marks the end. And then the difference between the two times, or no, actually the time since T1, so is the elapsed CPU time. Let me write it out in front. And it's probably better, instead of working with T1 and T2, to work with the time start, and here we have the time start, and that will give me the elapsed CPU time in seconds. Now wondering if it will give me the units. No, it doesn't give me the units, but this should be in seconds. So it took a while, so let me, for verification, so you can also check, so I now doubled it. So see how well this scaled. So remember, I had 1.8 seconds, and here you see that now it's 11 seconds. So just doubling the time gives me a lot more waiting time. So it's actually not going linearly. So let me mark that. So we tried 20,000 instead of 10,000, and the time went up to more than 11 seconds. Okay, so this is not yeah, we actually, I should have checked how many decimal places. Let me do that too. So if I ask for the symbolic sum of 10,000, so let's look at the value. Then you see that I have 314.1, but you know that it's 314.15. So actually I have 4 decimal places correct, but not 5. So this is a very slowly converging. It's not an efficient way to approximate, but it actually works well for our purposes. Okay, so we have something that is slow, so let's try to optimize it. Let's try to apply vectorization. So in vectorization, we apply Numpy. So from Numpy, import a range. We also import the square root. And I think there's also a range that we have to import. Well, a range is so what does a range? A range 10 gives me a sequence of numbers. So, and I can define this. So again, if the n equals 10, I can divide this by 10. So, and you see I have floating point numbers immediately, and I can subtract from that the 1. See, I have all numbers that are now smaller than 1. So the a range, perhaps I should have started at 1. So here we are. So I think this is in agreement with what I had here. So I started, okay, so this was n equals 100. So let me take 100. So I have 0.99 and I end with 0.1. Okay, so something is off here because I had the square. So let me assign this. So I had the numbers in the a range. Let me square them. So here we have now the numbers that end at 0.1. The a range, I think it might also have to end like Python at 0. So here it ends at 0 as well. Okay, I can take the square root of that. And that gives me an array, and I can take the sum of this and divide also by 100. So this gives me my approximation 4 times, and I get, so now let's change everything to 1000. And this gives me the formula. Again, we work with one formula, and I get here the code. So now I have my Python function. So experimentally, perhaps it went a little bit too fast, but let me try to build up the formula. So with what we did, so with a range 1001, we obtain 1000 numbers starting from 1 and ending at 1000. So the 1000 is included. So this vector is divided by 1000. We subtract from 1 all its values. So we subtract from 1 the squared values in the vector. Divide the vector by 1000 and then apply the square root. So I try to write everything in one sentence, but so the last steps are the summation, the division by 1000, and the multiplication by 4. So the last two operations are operations on scalars. So after the sum we get a floating point number. And speaking of floating point numbers, everything is automatically already with double precision floating point numbers. So here I must say that for this application we are interested in a floating point approximation. So it should also be said that we are using we are going much closer into the numerical analysis world. Okay, so let me now define the Numpy. We had the numeric symbolic sum, so now we have the numeric sum. So this is my Python function. So we apply the Numpy vectors. So in particular we apply the a range and the square root from Numpy, the Numpy arrays and vector operations to compute a numerical approximation for pi. So in some sense we are making things more efficiently, but I have to also point out that so to make this program, the function self-contained, I will import explicitly a range and the square root. So I was saying that we are going from the symbolic to the numeric. So often that transition, why people do this efficiency, is often one of the concerns. And also for this application, for this approximation here, it's not really worth it to work in a high precision. Okay, so let's first see that we didn't make any mistakes. So you see I get instantaneously the results. So let me now also do the Numpy numeric sum 1000 to time it. And last time I forgot to put strings around it, so let me put quotation marks around this. this is a string. And now you see that the order actually has, so I mentioned milliseconds, so this is microseconds. So the timing definitely has changed order. Okay, so let me do this for 10,000. So I have the timer that I start. So now it's important probably that you do everything in one cell. So not just so sometimes we would encourage that you split things out in multiple cells so you can check. But it's probably here, probably not probably, here it is certainly recommended that you would do the everything all at once so that there is no delay between you setting the timer and executing the function. So the elapsed CPU time, and perhaps I should now say that this was bit Numpy, so I had already an elapsed CPU time. So this is the Numpy elapsed CPU time starting from the timer that it has started. Oops, with 10,000 there is nothing there, so I have to a little bit so I do have only 460 milliseconds. So if I do this on 10 to the power 6. So I intended to compare this, but the 10 times more, so this will be, so while I'm explaining this, I can also go here for 10 to the power 6. So while I'm talking, so I have my elapsed CPU time here with Python, and here I have my vectorized. So the speed up is the time of the elapsed CPU time. So that was the time with the Python code divided by the Numpy elapsed CPU time. Now the elapsed CPU time, it has to be for the same dimension, and it has finished, so it's 13 seconds. So I can compute the speed up as a factor of 200. So we went from 13 seconds to 460 milliseconds. So it's a huge improvement. So this is a huge improvement. Okay, so there is an alternative. I can work with Cython. So what we do with Cython is that we start from the same. With Cython, we start from the same function, but add types to it. So the first obvious improvement is actually to work with floats. So let me copy and paste this. So I will add, so this is Cython, and then I have to add some decorator to it, so some directive that tell Sage that Cython code will come in. Now you see that the float, what happened to the float here is that the float happens at the very outside. So that is actually not very good. What I do better is to declare also the n not as a Python command, but I declare it as a long. So this is the first optimization that I can think of. Well, the other optimization was to move the float inside. So I have the argument, which is a float. So I will, on my equidistant points, I will do everything with the double floats. Okay, so when you click on this, so let me document what I did. The type information for the dimension was added. So we have the long n. And the type of the computations is changed to float. So in the symbolic way of thinking, we first computed all the symbolic argument, and then we did all the computation, did the transformation. So there is a problem. And what is the problem? Undeclared name or not built in. Okay. What's the problem here? Well, with Numpy, I imported the square root. So here I have to import the square root from the math library. So here I'm using also Python, but I'm going to run the square root on the Python objects. So let me document this because I forgot this. So observe the from math import square root, because with double floating point arithmetic we want to apply the square root function from the Python library. So what we did before in our symbolic Python, we had the square root of the Sage math library. Okay, so let's see if this is going to work out. So let me first check the correctness. Cython symbolic sum. That is not correct. That is very much wrong. So I'm now thinking what I did wrong. So the k divided by n is wrong. So actually I probably did the, well, no, I think I did the right type of division. Okay, so there's one thing that I can try, but so I can pull the float, the typecast in, and now it is correct. Okay. So what was happening, I was doing the k over n over the integers. So in some sense, I was thinking that this modification would not make any difference, but it did. It might very well be that the Cython is still operating with Python 2. I'm not sure if that would be possible. So let me time it, symbolic sum. So remember with Python we got microseconds. And here again we have microseconds, but it is a little bit higher. So I told already that vectorization was the most efficient approach for this example here. But still, it is of the same magnitude. I can still be a little bit better. What I can do is I can use we can use the square root from the standard C library. So now I have to copy and paste because I'm also a little bit running over time. So here you see the final result. So I'm declaring a separate external function, so that comes from the math library, so the header file math.h. And now I have the Cython sum typed. So if I now do, perhaps again, what I need to do, well, I copied it. So, but what I should have done is to check the correctness. So I'm skipping a step here. But since I'm copied and pasted, I trust that my implementation is correct. And now you see that by using the square root function, not from the Python library, but from the standard C library, actually I get a speed up of almost twice. So it almost runs twice as fast. Okay, final comparison is the timing. So I will copy and paste because I do not want that this recording goes over time. So I now time the Cython sum typed for the same dimension. Okay, so these are the modifications that I made. So let me run this. And you see it's almost instantaneous. It is not of the, well, it's still less than a second. So we see 125 milliseconds. And the speed up with regards to the Python code. So you see I had 46 milliseconds with Numpy. So the code is not as efficient, but one can also argue that these are actually small examples. So compared to the original Python code, we obtained with Cython 100-fold speed up, which is actually quite impressive, with essentially very little work. So which solution is best in absolute term here for this example? Numpy is, but that might not always be the case. So you see that with Cython code, the codelet's a little bit more technical, but we maintain the logic. So essentially we have this main formula, and what changed is the float here. And also I defined the type for k even, which I didn't do in the previous step, in the previous optimization here. So with Cython, so here we already got a significant speed up as well. I didn't time it. So, but you can think of, I think this might have been 40 or 50 times faster. So the best solution is with vectorization for this example, but this actually requires you, not in this case again, but still you don't have the for loop anymore. So the inner for loop was kind of folded into these vectorized operations. Okay, I'm running over time. I hope that this was interesting. So this 10th lecture uh, closes off the first steps, the first chapter in our course. So we've seen the basic numerical arithmetic, the difference between numerical and symbolic computation. We have seen complex algebraic numbers. In the middle part somehow of this first steps, and towards the last lectures we have covered more Python topics. So in particular for today, if somebody ever tells you that Python is simply too slow to be viable for scientific computing, then you have two arguments against that. So we have the vectorization from Numpy, and we have the Cython, which leads to 100 speedups, 100-fold speedups. So thank you for watching this recording. I hope this was interesting.